Okay, so who have we got here? What's your name?
Hello, I'm Kevin Kevin
From Bachelor of Engineering Honours, final year, and this is your project. And tell us what it's to do with power protection.
Correct.
Power. It's what is it? Power
protection system
for distribution grid with what's DG?
distributed generation.
Distributor. Yeah. So not being a power person, I'm a bit weak on this. But tell us a little bit about it. So it's for Tongan Island or something.
Yeah,
Is that right?
Tongan Island.
Just tell us about it.
So basically, it's a small system with 14 buses. There's the main generation point here. That's going to be, well, it could be an external grid or just a generation point, a
So
centralized
this is
generation.
in. What are you simulating it in?
Oh, I'm simulating in Power Factory, Dixon Power Factory.
Okay.
Yeah, that's the software that most power industry uses.
You also use MATLAB, can't you?
Yeah, yeah, yeah.
To MATLAB.
You can also use MATLAB, but Power Factory is a bit.
It's better,
It's a bit better, especially since.
So this
all
is
the
used in
features are
the
there.
industry, I take it. This
Yeah.
Yes.
Most of the industries do use Power Factory.
I see.
Europe.
Yeah, it's a bit difficult to do this on the bench.
No,
It's the sort of voltages are we talking about here? It's,
So the system voltage is 6.6 kV, so that's about medium voltage line in terms of distribution grid. But obviously in New Zealand, anything above 1K is considered a high voltage. But as it is right now, it's 6.6 kV. It's a medium voltage distribution grid. And also basically let's give you a little bit of a path information here. So this would be one of the paths, 23467, bus 23467, and these are the settings for the relays, overcurrent relays with directional components on it, and these are going to be the actual.
so tell me
fault
what the
count.
axes are, though. I'm not familiar with this. So the right.
Oh yeah, sure, no
so
worries.
so
This is a time overcurrent.
So this way, what's this x-axis?
X-axis from
Yeah.
here to here. That's going to be the actual amperage, the
current.
Yeah.
And
That's
this
going to
way
be the
is?
current. That's going to be the seconds, the time.
Oh, time in that. Oh, this is like
Yeah.
a chart recorder.
Yeah. So
Oh, I
this is
see.
a time overcurrent
I
plot
see.
for
I
the
see.
relays.
I see.
Yeah.
I see. Yes.
So you could basically see the relay reaction times, like 0.02 seconds,
Oh, I see.
0.22. So the reason why there's multiple graphs, well, multiple lines on here, is because of the fact that we've got multiple relays on multiple feeders. So what we need to do is we need to catch the fault flowing through at bus 7. Right? So initially the relay 6 to 7 primary should be tripping, and that's going to be tripping in 0.02 seconds. That's primary. And obviously the secondary is going to be the 6 and 7. The next one in line is 0.03, and so on and so forth.
Okay.
Now I've designed it this way to coordinate between the branches so that there's no unnecessary trippings.
So is this done in real life on software or PLC or something? How do you set up these times for the tripping?
Well, that'll be all done by the power controller for the relay settings.
Oh, I see, I see.
But obviously I can't really build the practical
Yeah.
thing because it's such a large scale, but
Okay.
I have been able to simulate these kind of things.
So there's some at the factory end or when you install it, you can set up all these times and things on the main controller.
Correct.
Is that
correct.
done through a SCADA system or something maybe? Or
Yes, you would be able to use a SCADA system, but
Yeah.
at the moment, we're not actually doing, well, from my designs anyway,
Yeah.
we don't really have that kind of communication between the relays.
Yeah.
So it'll just be working on itself. But if you're implementing in real life, you could make it coordinate between.
So then you could change
relays.
the timings later if you wanted to.
Yeah, if you wanted to, but
Yeah.
the reason why I didn't do this on this is because of the fact that the voltage is quite low, with 6.6 kV, and the fact that it's not a large system, it's only a 14 bus system. So there's no need for any kind of coordination between, there needs a coordination, but we don't really need an actual communication between the relays themselves.
Okay, continue then. Sorry to
No,
interrupt.
that's fine. So this is simulating the fault at bus 7, and I'm pretty sure in saying this is the three-phase fault. Just quickly check. Yeah, three-phase fault. All these going to be different if, let's say, there's a line to ground fault. Just the most common. Wait, what? That's a bit odd.
That was the other thing I was
I've changed the settings before.
No one's living in that house for like 2 weeks. Yeah. And it's something that I'll put in my further design.
Yeah, I don't know what the hell's going on here.
Share.
It was working well.
That's okay.
But, oh,
Interesting to see the software working.
yeah, I know, right? It's a bit odd though. So it was working. Oh wait, phase to neutral to ground. I need to do a single phase to ground.
My plan is something
Which is going to be this one. There we go. That's it.
Okay.
Right. Okay. So this is going to be the currents, and yeah. You can obviously see the coordination between them. 0.04 seconds, 0.5 seconds. So same kind of deal. But yeah, that's pretty much about it. It's able to detect any kind of fault on the system themselves and isolate it as fast as possible. The times that I've set it to be is around 0.02 to 0.05.
So your system works okay then, basically. Then excellent. All right, thank you for that.
No worries.